In this video, we will be looking at the projectile motion of a paper ball. The purpose of this lab is to compare a position versus time graph of x and y of a projectile being thrown to a computational model of that paper ball being thrown with simulated drag and no drag. So the principles used, we use Newton's second law, the velocity update and position update formula. So we have my code here, which is the velocity is F net over ball, mass of the ball times delta t, and then we have the position is the position plus the velocity times delta t for position update. And we also have the force of gravity and drag. So we have F drag equals negative b, which is a constant we will use, velocity squared over velocity hat. And so here's the video being played. And so with this tracker graph, we can see the x position versus time. What I did was I started at the height of the ball's motion. And we can see here x position versus time is linear. And in fact, it is going to be linear throughout the models that are shown today. And the y position versus time, it starts at the peak and then goes all the way down to 0, or approximately 0. And so the computational graph here, you can see the GlowScript code that was used. And the assumptions made is that the initial velocity is the first step in time. And I found through using different b values that b equals 0.015 produces realistic motion. And anything not in the hundredths place, anything in the tenths place actually produces a model that is pretty wildly far from what was actually shown. So the lower it is, the better it is, because a paper ball isn't going to produce that much drag. And so for the GlowScript code, here we can see that the mass of the ball is around 4.7 grams. And the initial conditions, we have the position and velocity vectors. We started at time 0.4. And of course, gravity is 9.8. And so for the results in analysis, we can see that with drag, it takes a little longer to reach 0. Actually, it never ends up crossing 0. And with no drag, we can see it's a little quicker to go down. So what this means is that without drag, the velocity versus time graph shows a straight line, meaning that the object accelerates continuously due to gravity with no terminal velocity. And with drag, the velocity initially increases but then levels off, meaning that the object reaches terminal velocity when the drag force is balanced with the gravitational force. So what if? What if the object was initially thrown straight up with the same initial speed as in our experiment? So what would happen is that the time would be longer because the object must first decelerate to 0 velocity at its peak before falling back down. And using kinematic equations, the time to reach the peak is a little longer, and the time to fall back down is the same with no drag present. So what would happen is that the after we reach the peak, the graphs would model each other as they did in my slides. But if you look at the overall position x and y starting at 0, what it would be is that it would take a lot longer to reach the ground level. So the y would look different, and there would be no change in x because it's thrown straight up. So with drag, the upward motion is a little slowed more than free fall, meaning the ascent takes longer than the descent, further increasing total time. And if we compare the original experiment where the ball was only moving downward, then the thrown up case must take longer due to the additional phase of motion. Thank you.